Good morning, everyone. I hope you can hear me. We're going to start the webinar in a couple of minutes. Let's wait for the last people to join us. So good morning again. I hope you can hear me all. Thank you for joining me at the first Battery to Life webinar. My name is Maria Cherivoti and I'm from ICCS. I'm the Dissemination Communication Manager of the project. This webinar marks a key moment for the Battery to Life project as we share with you the most mature key exploitable results we have developed so far. Before we begin, let me briefly walk you through today's agenda. I hope that you can see my screen. We will start with a short introduction to the Battery to Life project by George Konstantinidis, the day-to-day project manager from the coordination team ICCS, and an introductory presentation about the key exploitable results from Frida Kuhl from Etelatar Innovation. These two presentations will help set the scene and the context for the results that you're going to see today. Then we will move to the core part of the webinar with presentation of the second life battery sizing tool by our speaker Isaskun Aispouroa from Civitec, the state estimation of cylindrical cells using pressure and strain sensors by our partner Gregor Glantz from AIT, Austrian Institute of Technology. And we will conclude with our last speaker, Sotiris Efterpiou from Sunlight Group, presenting the quality control procedures, disassembly handbook, and disassembly of used batteries. After each presentation, as you can see the agenda, we will open the floor for a short Q&A session where you will have the opportunity to interact with the speakers. However, we encourage you to submit your questions at any time using the Q&A feature that you can find in the upper right part of the platform, indicating the presenter you're addressing, because we're going to answer all the questions. Even if we don't have the time, we're going to have a follow-up mail and answer all of your questions. I remind you that the webinar the total duration of the webinar is it's a bit more than an hour and 15 minutes. And the recording and the presentations will be available on the project website very soon. So with this, I think that we can start. I will ask George Konstantinidis to share his screen and start. George?
We cannot hear you, George. You are muted.
Yes, sorry. Okay. Thank you, Maria. I was asking if you can see my screen now, my presentation, right? Yes. Thank you for your
Yes, we can see
confirmation.
that.
Yes, so good morning, everyone from my side, and welcome to the first BATTERY2LIFE webinar. My name is George Konstantinidis from ICCS, and it is my pleasure to open today's session on behalf of the consortium. Today's webinar marks an important milestone, as Maria said, for the project as we move from research development towards impact by presenting mature results that support the safe and scalable deployments of second life batteries. Let me briefly introduce Battery2Life. You can also find this information to our website. It is a Horizon Europe project running from 2024 to 2026, bringing together 11 partners from 5 countries with a total budget of approximately 4 million euros. The project is coordinated by Dr. Angelos Amnitis from ICCS, and I'm responsible for the day-to-day project management and coordination activities. Battery2Life address both domestic storage in Austria and industrial grid-scale storage in Greece, ensuring that the solutions we develop are validated in a real operation environment. To understand why Battery2Life exists, we must consider the rapid growth of electric vehicle batteries reaching the end of their automotive life. By 2030, it is estimated that more than 5 million EV batteries will no longer be suitable for automotive use. However, this does not mean that they are technically exhausted. At the end of warranty, EV batteries typically retain 70 to 80% of their nominal capacity. This residual capacity represents a major opportunity for stationary energy storage applications and for supporting renewable energy integration. However, there is also the challenges. There is uncertainty in battery conditions, remaining lifetime, safety behavior, and lack of standardized processes for assembly, disassembly, and reconfiguration. Without addressing these barriers, second life deployment cannot scale safely or economically. Battery2Life was launched to directly address these challenges. The project aims to enable the safe and reliable transition of batteries to second life applications. We focus on developing open, adaptable, and intelligent battery management system tailored specifically of second life needs. At the same time, we support efficient reconfiguration and reuse of batteries in stationary energy storage system, ensuring both technical reliability and economically feasibility. To achieve these objectives, Battery2Life develops a set of complementary innovations. This includes advanced diagnostic tools for second life batteries, as well as generalized sizing tools that help determine the most appropriate configuration for reuse. Beyond tools, the project also contributes to intelligent BMS battery management system solutions that supports safe monitoring, control, and reconfiguration of battery system in their second life. And together, these innovations form the technical foundation for reliable second life deployment. An essential aspect of Battery2Life is validation through real business cases. The project includes two complementary demonstration environments. First, the utility scale storage application focusing on efficient reconfiguration and reliable large-scale operation. And second, a domestic storage application where new battery design principles are assessed in a residential context. These business cases ensure that the solution developed within the project are tested under real operation conditions, addressed not only technical performance, but also economic and practical feasibility. This webinar is the first in a series of dissemination activities within BATTERY2LIFE. As the project progresses, results will continue to mature toward higher TRL, technology readiness level, contribute to standardization efforts, and support market uptake and real-world deployment. We will have time for questions as also showed in the agenda at the end of each session. And with that, I would like to hand over to our next speaker, Frida from Telatar.
Hi,
Thank you very much.
George. Yeah, I can also share my screen. Thank you for the introduction. Hello, good morning also from my side. My name is Frida Kuhl. I'm the CEO of Telatar Innovation, and inside BATTERY2LIFE we have the challenging role of managing all the exploitation and business modeling activities. I say challenging because in research projects it's always quite difficult to bridge this gap between basic research, building prototypes, and then to market strategies. So today I'm going to give a general introduction into what are key exploitable results and how we are dealing with different kinds of key exploitable results in the project. Just to lay, let's say, a baseline for the key exploitable results that we're going to talk about, it's important to keep in mind that in the project we have, I think, 20 in total, 20 key exploitable results. And I'm going to explain how we identified them. But today we're just talking about 3 of them because they have already reached the maturity inside the project lifetime. So let's start by explaining what is a key exploitable result in reality. Usually we have already a predefined list at the proposal stage. I think many of you are familiar with EU projects, and they attempt, let's say, to map all the main outcomes or knowledge generated by the project. Usually they are owned by different contributors that contributed to the knowledge or the result, but they can also be owned by just a single partner. Inside BATTERY2LIFE and in our own company's methodology, we make an important distinction between commercial and non-commercial key exploitable results. Non-commercial results can be, for example, have these exploitation routes that are mentioned here, like societal, political, or public knowledge, and can be exploited in different activities that don't always require, for example, transactional interaction or compensation, financial compensation. And usually a key exploitable results prompts at the end of their maturity, when they have become relevant inside the project or validated, they prompt some kind of action. So either we are going to launch a final product or also a subcomponent of a product. We have improved some kind of process. We are offering a new service. We contribute to standard, or we shape a policy, or we just publish, for example, knowledge. We share knowledge in open access. So this is the different kinds of key exploitable result that you can consider inside an EU project. We have listed all of them. I don't know if we have the time to get into all of them, but just to explain to you that this is the process we have followed in BATTERY2LIFE also, to expand the list of key exploitable results from the proposal stage. So instead of just considering, let's say, the traditional ways to just consider the products that come out of the project. What is the prototype or the algorithm or the final product, or what is the main result of the project? But we have also moved to include more intermediary steps. Let's say, for example, methodologies that we develop during the project that eventually lead to an improvement of a process. We have also considered from our data management plan all the different kinds of data sets, repositories, libraries, because they all constitute some kind of knowledge that we can share beyond the project lifetime. They may be non-commercial key exploitable results, but they are important because they are pieces of knowledge that we can share and exploit in a different way than a commercial exploitation. Then, of course, we also have standards and guidelines. For example, the handbook that Sotiris is going to share later is one of these that is also some kind of very practical knowledge sharing that we can share either to the standardization bodies or to the industries to share our process and also share openly wherever or not it's successful. And of course, finally, there is something more abstract, which is policy, regulation, and social engagement. This includes recommendations to, for example, to the Commission, but also to the research centers, to the Parliament, to different kinds of bodies, white papers, and more general, let's say, roadmaps on how we can achieve what George has mentioned, like how can we actually achieve that automotive batteries effectively reach a second lifetime. So for the commercial cares, which is the more easy part, let's say, because I think in our minds it's very easy to comprehend. We develop something and then we make a product from it and we sell it on the market. For commercial cares, that in our case is mostly the actual like first life batteries, so the vehicle batteries, but also the second life applications. So for example, the grid energy storage cabinet and so on. What we do is we analyze the market and the value chain. So what is the size of the market? Is it saturated or not? What differentiates our product from other products? Do we have freedom to operate? Are there any patents that are blocking the way? And also, what are the standardization requirements? What are the certifications we might need to obtain for the new product to actually launch it to the market? Then we can position the product or the care accordingly. So we can make a pricing strategy. For example, we can check what needs to be the actual price of the product compared to the costs that we will have, including also, for example, learning curves and scalability. And finally, also position our intellectual property rights. So will we apply for a patent? Will we apply for a copyright? And make a kind of strategy. And this positioning helps us to understand if it's worth to launch the product or not. And then comes the exploitation. So we actually draft the business model. We make an actual go-to-market strategy. We actually identify our customers. We make a funnel from them. We contact them. We ask them for feedback for early adopters. We make a roadmap, like in 6 months, we want to be able to sell the product. And of course, we scale up the production if we find that it's worth it and that there's market feedback. Now, for non-commercial cares, it's a little bit more complicated because often this is something that falls more under dissemination in EU projects, but actually it's a bit the same, like disseminating and exploiting non-commercial cares is more or less the same. It's a way of sharing our knowledge without necessarily selling a product or a service. So in this case, we have some different examples. We can share it to advance human capital. For example, providing training contents. This can be for universities. This can be for like providing, like mentioned here, like free programs or tools, like for example, opening our repositories and allowing free access to some training models. Can be MOOCs like Coursera or these kind of platforms for free courses. Can be in-house training for other companies, different activities. Then we can build networks. So for example, we have a stakeholder community that we can keep alive, and we can keep feeding bidirectionally knowledge from their developments and from our developments, and keep these communities alive beyond the project lifetime. This is, for example, sometimes how also big EU platforms are formed. We can also create something like innovation hubs, working groups in standardization, but also in, let's say, pan-European organizations, or we can contribute somehow to research infrastructure. And then, of course, the classical communication dissemination. So publishing papers, handbooks, tools, making some kind of communication campaigns, and sharing our outcomes. And then I'm going to wrap up here because I don't want to bore you too much before we actually jump into the results. But just one important thing about IPR. So I think this is something that in most EU projects people neglected a little bit because it seems like something that will happen long after the project ends. But it's something that we actually already address in the project level. The different levels of intellectual property rights is a patent, which is the holy grail of IPR, let's say. But it's very difficult to obtain, it's very expensive. It can take some years, it can cost several tens of thousands of euros. So it's something that maybe we don't expect to happen inside the project lifetime, but hopefully at least to initiate this process. Then more easy, for example, to apply is copyrights, is trademarks, is industrial designs, trade secrets, utility models that all protect some kind of a part of the product, let's say. And also we clarified the ownership. So something very important that I like to highlight at this point is that protection does not, ownership over IPR does not mean that it's protected. So what we help the partners to do inside the project lifetime is we help them to identify the intellectual property, to understand which part of it is actual intellectual property, to manage it, so to understand who co-owns it maybe and how we can find an agreement in case there's a conflict, and to protect it. But afterwards comes also another part, which is the enforcement. So to monitor actually what's going on in the market and to identify in the moment that somebody is violating the IPR. This is a very complex process that sometimes is not very easy, but we can also help the partners to find some kind of tools, for example, that help them to monitor this and that flags for them. For example, this competitor has launched a competing product or might infringe your IPR. Please check it and take these necessary steps to protect your IPR if possible. Okay, and with this, I conclude. We have, like I mentioned, many cares in Battery2Life, 20 in total. You can see some of them there. Some of them are not validated yet, so they are not part of this webinar, unfortunately. But the most important ones is the sizing tool that Isaskun is going to present, some experimental results, and also we already have one handbook. So I think I'm handing over to the next speaker at this point. It's Isaskun, if I'm not wrong.
Yes, thank you, Frida. I will share my screen. I hope that you can see it. properly.
Yeah.
Yeah, thank you. So as Frida told you already, I'm Itasco. I'm coming from CDT, and I'm going to present you in this webinar the battery diagnostic and sizing tool we developed during this last year. So moving forward, before starting with the tool itself, I wanted to present briefly CDT to the ones that don't know us. So we are a research center located in the north of Spain, in the Basque Country in San Sebastian, more specifically. And actually, CDT is composed of two different entities or sectors, let's say. In this case, they would be surface engineering, and the one in which I am part of is the energy storage. And as you can see in the right side, we have recently moved to our new testing and main facilities of the energy storage laboratories. In CDT energy storage, we cover mostly all the value chain of the battery, as you can see, starting from the battery materials until also end of life. So you can see there also that we have some spin-off in different phases. For example, we have CDCell for cell manufacturing. We have also OBS as BMS designer. We have Lanto that it's prepared for space batteries, and also Kudeva that manage the, let's say, end-of-life reusability, recycling, and also repairing. And in parallel, we have the activity of the battery testing and also modeling. This would be like a brief summary of what we can do. And in this context, we are part of the BATTERY2LIFE project, and we developed this second life battery sizing tool. For that, we faced some challenges. The first of them would be actually to promote the circularity and the use or reuse, in this case, of end-of-life batteries. We can call it also end-of-first life in this case, because we are trying to promote this second life. We want to facilitate the integration of these second life batteries, as we see that they are a good sustainable solution in this energy transition. We want to, by this tool, optimize the battery sizing by comparing different application and strategies. And at the end, what we want it to be also is easy to use for both end users and also manufacturers. This way, we propose this battery sizing tool, which is actually composed of two different phases. And the first one would be the diagnosis phase, because as you may know, we are basing on end of life, in this case, as mentioned, end of first life batteries to build this second life system. So we first need to diagnose the available battery units. This phase actually is we build it by combining two different models. The first one would be the data-driven analysis, and at the end, what we are here doing is analyzing the last month of operation of this first life based on historical data, and we try to identify some valid or significant cycles of the operation, and this way we can define the round trip efficiency and the state of health of each battery unit we have available or identified in the end of first life. Then we combine this by a test-based evaluations, because at the end we cannot base only in historical data, and we need to really test those battery units to check if they are valid or not for a second life. We proposed 3 different tests that we can cover the evaluation of different parameters, for example, the capacity deviation or the existence of the lithium plating. And this way, what we do is define if each battery unit is valid or not for a second life. That combined with the list of state of health and round trip efficiency values, what we have now is a list of end-of-life battery units that can be chosen or used for the sizing a second life system. And in this phase, in the phase of sizing, we have 3 internal steps. The first one will be to propose a sizing. Here, what we need is to input some demand and generation profiles if they are needed. And we also evaluate the application requirements and specification. From there, we identify from one side the peak power demand of the system as power requirement, and then we identify the energy requirement. In this case, we have 3 different possibilities, which is to evaluate the daily excess of the system application, also to evaluate the charge period or the accumulated energy balance. Based on those, we identify the need of power and need of energy, and what we do is choose the battery units from the list we have, and we build or we propose a sizing for this second life system with a specific configuration. But we need to validate this initial sizing. So what we are validating now is the operational limits, and this way we check the voltage range, the current limits, also the life expectancy and the full equivalent cycles. This way we can define if those limits are respected or not, so we can validate the technical feasibility of this solution. If not, if we find some limits that are overpassed, we should go back to the initial sizing and make it less restrictive. In case we have a good technical validation, we continue in this case to the economic analysis. And here at the end, what we do is to take the proposed sizing of this system, and we evaluate it economically. We check the life expectancy and also the maximum CapEx that it could have, this second life system. And this way we can evaluate the feasibility of this second life battery. So with all of this, at the end, what we obtain is an adaptable and scalable tool that we can adapt to different scenarios, applications, and even battery technologies. This way, we are able to improve the reliability of the second life battery systems in order to promote their usage in the market and final solutions. We also want to promote, we hope that we can promote the reusability of the end-of-life batteries for second life applications, and also we could improve by this the traceability during this end of first life until this second life. And with that, I will finish. If you have any question, I would try to answer them. You can also reach me otherwise by email for any question. Thank you very much.
So if there are any questions, please raise your hand, or you can write the question in the chat. I can see someone. Yeah, let me, okay, please raise your hand and I will unmute your mic. I think, Mr. Wurum, we can hear you. If you can, please.
Yeah, can you hear me now?
Yeah.
Yeah,
Yep.
okay, yeah, perfect. Thank you. My mic looked like it was muted for a long time. Yeah, thank you for your presentation. My name is Frida Willem-Brøer. I work in Sintef in Trondheim. I have a question. When you do this sizing and you kind of estimate the size of the battery according to the profiles, energy profiles, what kind of a state of charge window do you estimate for these? Like, do you go full 0 to 100, or like what kind of I mean, normally you don't, but do you have any sort of standard that you use for state of charge windows when you do the sizing?
Yeah, actually, we can define all of those parameters in the tool. You can define which is your maximum shock and minimum. You can define your system voltage and so on. So at the end, it's up to the end user to define those limits. But we usually limit the shock range to between 10% and 90%, considering already the state of health. I mean, it wouldn't be related to the initial whole capacity, but let's say the actual capacity. So it would be adjusted to the real state of those battery units.
Okay, yeah, thank you. That actually also answered my second question. Thank you.
So if we don't have any other questions, I don't see any other hands. Thank you, Faskun. We can move on with the next presentation. Gregor, you can proceed.
Yes. Hello, everyone. Can you see my screen?
Yes.
And you can also hear me. Perfect. So, hello, everyone. My name is Gregor Glanz. I'm working at AIT, at the Austrian Institute of Technology. And one key exploitable results from AIT side is the state estimation of cylindrical cells using strain and pressure sensors. However, due to the limited time frame today, I will be only focusing on the strain sensor part. And to start my presentation, I would like to give a bit of a motivation. And in general, the state of lithium-ion battery in a pack is determined with the electrical two-pole behavior. This means that the battery management system measures the voltages, currents, and temperatures. And however, the mechanical state of the battery is rather difficult to determine based on these electrical properties. For example, you can see here on the right side my swollen laptop battery, and the BMS of my laptop said everything is working perfectly fine. I at one point realized that I can't close my laptop anymore, and it has a very ergonomically shaped keyboard. And with these additional sensors that I'll be talking about today, these kind of mechanical properties and their changes can be detected, and also safety critical states like swollen laptop batteries could be detected. So, and how we can detect this, looking into the theoretical background. So lithium-ion batteries undergo mechanical property changes during their cycle life. There are reversible changes and irreversible changes that occur during charging and discharging. And the main changes regarding volume expansion, let's say, is coming from the anode, from graphite, because between a fully discharged and charged state, it expands up to 10%, or even actually more if the anode material is doped with silicon. And the idea how we use then strain sensors to measure these changes is maybe I can have here some pointer. I could find it. Yeah, is to measure the strain on the surface of the cell. You can see here how the inside of a cylindrical cell looks like with the jelly roll and the active material inside. And when this jelly roll expands during charging, it also presses against the cell housing, and we measure this basically expansion or deformation of the cell housing with a linear strain gauge. And what we expect based on literature is that during the charging, we measure an increase in the measured strain, and during the discharging, we measure a decrease in the measured strain. And our question that we asked ourselves at the beginning of this project is if we can correlate these strain measurements with SOC, and if this method in general works. So I already mentioned we applied a linear strain gauge in the discharge state on the cell surface, like you saw it in the previous picture. We measured the circumferential or the hoop strain, and all of the measurements were conducted in a climatic chamber to minimize the environmental temperature influence. And we also, of course, tracked the surface temperature of the cell with a thermocouple. And we used an amplifier from HBM in the quarter bridge configuration. Here on the right side, you can see our overall setup, and recycled the cell and measured basically the strain together with the electrical values from the battery with our battery cycler. And one of our cells, we in total looked at 2 different cells in this project, and one of our cells that we looked into was the Samsung 35E cell. It's a 18650 cell, and we placed the strain gauge in the center position, and we conducted the measurements at the beginning at room temperature, but we varied the C rate with 0.1 C, 0.5 C, and 1 C. And on the right side, you can see on the bottom plot, you can see basically our charging profile. And on the top plot, you can see on the left-hand side the measured strain in green, while on the right side, you can see the surface temperature of the cell. And we measure basically what we expected. During the charging process, we see an increase in strain, and during the discharging process, we see a decrease in strain. And this is very consistent. And the only thing that we observed is that during higher C rates, we also see an increase in the strain values, but this is most likely due to the higher surface temperature of the cell, because strain sensors or strain gauges are very sensitive to temperature. And we tried different positions as well along the axis, and we saw a very similar strain behavior with an almost constant shift between, for example, here the center position and the bottom position. So, and we also did obviously multiple cells of this type, and they all show a very similar and consistent behavior. However, coming now to the second cell type we investigated, this is the Samsung 29E cell. It's also from the type 18650. And we again placed our strain gauge at the actual center position, as you can see here in the schematic plot. And we did some very similar measurements. And for the 0.1 C charging and discharging rate, you can see here a decrease in strain and an increase in strain during discharging. So basically the exact opposite or inverse strain behavior that we saw previously. And this strain behavior, however, does not align with the underlying electrochemical theory, and we even measured some negative strain. So we also tested multiple cell positions, and at one point we measured this expected behavior once we put the strain sensor on the bottom of or close to the negative pole of the cell. And you can see that during the charging, the strain values, the surface strain increases, and during discharging, the surface strain decreases. And we did then this same position on 3 different cells, and these showed again then different results. So what we concluded out of this measurement with the Samsung 29E cell was that there's very different strain behavior, and we cannot basically get the consistent strain measurements on this cell type. So our thought was something in the internal structure has to be different. So we did an post-mortem analysis of both cells to compare them with each other. And we opened these cells in the glove box, and our idea was maybe the tabs are differently or different aligned, but overall they're both manufactured from Samsung, and they have exactly the same caps and the exact same widths and heights. So then we thought, okay, maybe the material is different. So we did some XRF measurements on the anode material, and we saw that for the 35E cell, silicon is present, while for the 29E cell, no silicon is present. And this gave us an idea that most likely due to the present silicon of the 35E cell, it has a more uniform expansion. We also conducted CT scans in the discharge state, and you can see on the left side the 35E cell and the jelly roll in the middle position, and you can see that there's only a very small gap between the housing and the active material at the 35E cell, while for the 29E cell we see many multiple gaps actually, and they're also much larger than for 35E cell. So the packaging of the 29E cell is not as ideal. And our conclusion was that the combination of the silicon and these no gaps calls for this much more uniform and non-position dependent strain results for the 35E cell. So we saw basically with our strain gauges that we applied some manufacturing differences and also material differences for these two cell types. And another part of this project were overcharging tests. We conducted them for the Samsung 35E cell, and we overcharged the cell with strain sensors equipped with 0.5 C until the current interrupting device is activated. And you can see here in the top subplot the charging profile. The green line represents the cutoff voltage of 4.2 volts. In the second, you can see the surface strain measured. And in the last subplot, you can see the surface temperature of the cell. And what I want to highlight here is that the green line at 4.2 volt represents the strain measured at the cutoff voltage, while the red line represents the point in time when this maximum strain is exceeded. And it's clearly visible that this red line occurs much prior to an increase in surface temperature. You can also see it here by the steep increase in microstrain much prior to the surface strain. And this is one of the highlights that we experimentally proved and measured in this project, is that the strain increases exponentially prior to the measured temperature, and this allows a detection of the safety critical condition with strain gauges prior to temperature sensors. And then I think my time is almost over. Coming to the conclusion, what are the main things we did in this project or with these measurements? We saw that the correlation between strain and SOC is not possible for all cell types. For certain cell types, like for the 35E cell, it's possible. We also developed in the project a machine learning estimator. What we also saw is that the used active material, the packaging, and the manufacturing processes are crucial for measuring reproducible strain results, and that with the help of strain gauges, overcharging or safety critical events due to overcharging can be detected prior to standard temperature sensors. And I think with this, I will conclude my talk. Thank you very much, and I'm happy to answer any questions.
So I can see that we do have 2 questions in the chat. Can you please check them, Gregor? If you open the meeting
Yes.
chat, you can see 2 questions. Okay.
One question is did you check whether the geometry changes elliptically instead of full diameter increase? We did not check this, to be honest, because there is one publication online that uses also an 18650 cell that talks about the potato effect, where they used some triangulation measurement to see the deformation across the circumference, and they state that it's not uniform. And we saw some small deviations based on the sensor position when we positioned it at different, let's say, angles at the same actual position. But we cover quite a lot of surface area. So the strain gauge has around, I think, like 10 millimeters length. So we cover a significant amount, so that the differences are not that big based on the circumferential position. I hope I could answer your question with this. If you want, we can connect, and I can also send you this paper regarding the non-uniform measurements. And then the second question is, how would you expect the strain sensors to work for pouch cells? For pouch cells, we did not implement it yet. We were thinking about it, but it is a bit more difficult because pouch cells expand in the thickness direction, and I can only or to place a strain gauge in the thickness direction of a pouch cell is rather difficult, because I have a very small surface area where I could place them. And in the surface direction, let's say, of a pouch cell, the expansion is rather minimal. So in order to implement them on pouch cells, I think there need to be some more elaborate strain gauge, let's say, so that you can measure this in the thickness direction. So I think for pouch cells, it's more difficult to measure this expansion with strain cells. I think there are other methods like pressure sensors more suitable to measure the expansion. I hope also I could answer your question.
Okay, and I think I can see hand raised. Okay, let me try to unmute. Okay, I think that we can hear you now.
Does it work? Can you hear me?
Yes.
Oh, perfect. So first, thanks. That's, I think, some cool and practical research results. I have two questions, actually. I was wondering first, for the extreme example, for example, the laptop battery, where you have like very extreme swelling, I was wondering if it wouldn't be possible to also detect this by like the electrical two-pole behavior, because I would imagine you would see a rather sharp increase in maybe like cell resistance impedance compared to maybe the aging. Like, do you have some insights into that?
We did not cause any. I mean, I work in this kind of abusive testing for some time, but we did not cause, also not for this project, some dedicated swelling and try to detect the swelling process with mechanical sensors. So I assume that with strain gauges it would be possible if the cell swells like this, and I put it on the surface. But I don't recall seeing any big changes. But it's been some time since I did some swelling tests, let's say. So I'm not up to date on this regard. I just checked the laptop information, and there it says that my battery is working perfectly fine. So I guess it's possible to detect it with electrical states, but it's at least not implemented in this matter.
Yeah, makes sense. Okay, thank you. And then my second question to that would be, because I would imagine that it's quite significantly increase in like the cell assembly cost to add to each cell like a dedicated sensor to measure these mechanical parameters. So I was wondering in which direction, like, is there any industry interest in that, and or like, is there a way to kind of transfer that into practice? Do you have something for that?
I mean, we were also talking with our industry partner MIBA a bit when we were writing this proposal, and they were thinking, or we were thinking together, that it might be replacing a temperature sensor, for example, this strain gauge, because the strain gauge is also temperature dependent, and by doing more improved tests, it would be possible to also get the cell temperature out of the strain gauge measurement in the normal behavior, let's say. So eventually in safety critical applications and substitution of temperature sensors with strain gauges to reduce costs might be one application to use this kind of technology.
Oh, that's super interesting. Thank you very much to that. Yeah, I might reach out for that, because that's yeah, sounds cool. Perfect. Thank you very much.
So thank you. If you've got any other questions about Gregor, you can write them in the chat, because we have to move on. Thank you, Gregor. Sotiris, whenever you're ready, you can start. You can proceed with it.
Hello, everyone. Can you see my screen?
Yes, Sotiris.
Okay, perfect. Hello, everyone. I am Sotiris Efterpiou, a research engineer from Sunlight. Today, we will speak about the quality control procedures, the disassembly handbook, and the disassembly of used batteries. First of all, let me tell you a few things about Sunlight. Sunlight is a global battery manufacturer producing lithium-ion and lead-acid batteries for traction, mainly forklifts, and also energy storage systems. Then we will proceed to a short summary. First of all, the project, the goal of Sunlight is to build a second life battery for energy storage system, utilizing batteries used in forklifts from our existing customers. Today we will see today's presentation will begin with an overview of our quality control procedures and incoming inspection methodology aligned with UL 1974 requirements. We will then introduce disassembly methodology in steps as described in handbook. And finally, we will highlight the key steps from the disassembly process. So, here we can see an overview of the refurbishment methodology. The first step is the battery selection. First of all, we have to select the batteries based on the criteria we can see, which is the operation history, performance metrics, and other ones we will see later. The second step is the disassembly step. Remove all the components from the battery pack. We have to remove them. The third and most important step is the mechanical, electrical, and electrochemical evaluation. In this step, tests on mechanical, electrical, and electrochemical level need to be done to ensure the safe use of the battery in second life up. Also, in this step, we have to decide which modules we will use in second life battery and which modules we are going to discard. After that, the approved modules we proceed with the remanufacturing process. We have to build the battery, and the final step is the use of the battery in second life application. So then we will see the quality control procedures, a summary of the quality control procedures. First of all, the selection criteria of the battery is most importantly the state of health of the battery pack, and if this state of health fits to our second life application, the operating hours, and the location of operation. After the selection of the battery, we have the incoming inspection and evaluation, to which, first of all, we do some dimension measurements of the modules and outer dimensions to access potential changes, for example, swelling or something like this. Then we do some visual inspection for cracks, damages, and other faults in the enclosure of the battery, the module, and all the components. After that, we have some electrical tests, open circuit voltage measurement to ensure that it is within the limits, high voltage isolation check to ensure that we don't have any isolation problem, capacity check to see if it fits to our application, internal resistance check, and then we activate the battery by charging discharging it for one cycle. We also measure the temperature, voltage, and current of the cells and modules. We will proceed to disassembly methodology as will be described in the handbook. So the disassembly methodology are in two levels. First of all is in battery pack level. The steps below are presented with are presented as we will do these steps. First of all, we have the initial mechanical and visual inspection. It's a full assessment of the battery pack structural integrity, including checks for casing damage, cracks, and corrosion on ports or terminal. This is according to UL 1974. After we do some electrical testing, as we said, the activation, the first electrical test we do is the activation with charging and discharging the battery. Then we do the capacity check according to IEC 61960 standard, and a cycling to monitor the temperature, voltage, and current. After that, we open the battery enclosure, by removing the side plates to have internal access in the battery. Then we disassemble the wire and other subsystem. We remove all wiring interfaces, including cables, connections, connections between the battery modules, the BMS, the master board of the BMS, and all other internal subsystems. After that, we have again electrical testing, measurement of the battery open circuit voltage, isolation resistance, and ACIR, AC internal resistance. After we have the module and control panel decoupling, we remove all the interconnecting cables between the battery modules and the control panel interface. We remove the bolts, brackets, and components used to fix the modules within the enclosure. And the final step is the on battery level is the module extraction. We remove the modules from the enclosure. All these steps represent the reverse sequence of the assembly procedure. So we do some kind of reverse engineering. The second level of disassembly is the module level. The majority of the steps are the same. We initially do a visual inspection for cracks and damages. Then we do a dimensional measurement of the module to check again if we have cell swelling or something like that. After that, we do some electrical testing, which self-discharge, capacity verification, and cycling with the measurements mentioned before. Then we remove the top plate of the module to access the cell. We have a detailed check for BMS burn marks, damaged wiring, electrolyte leakage, which is very important, and discoloration in insulation films. After that, we remove the BMS of the slave unit inside the modules. We do an inspection for cell swelling, terminal corrosion, and burn marks. And then again, electrical testing, measurement of open circuit voltage of the cells, evaluation of AC internal resistance and DC internal resistance. This procedure used for enables the accurate module sorting and grading. The rejection thresholds varying among manufacturers and application requirements, as mentioned in UL 1974. After the second electrical test, we have the removal of the bolts from bus parts and cell terminals to detach all the remaining cables. Then we do a lithium plating test and to detect lithium plating. And that's a summary of the disassembly methodology. Finally, we will mention some key insights of the disassembly methodology, which are the reverse engineering of the original assembly steps to ensure that we have a straightforward disassembly process. The integration of the second life adaptability criteria, focusing on manufacturing process and assembly drawings during selection, and the mechanical and electrical tests to ensure that only safe modules will proceed to second life applications. So thank you. if you have any questions.
Thank you, Sotiris. If there are any questions, please raise your hand or write your question in the chat. I think you had everything covered, Sotiris. Okay. Okay, I see that somebody can't raise their hand for some reason. Okay, let me see. Okay, I'll try to unmute you. Let me find. Okay, we do have a question. Can you see it in the chat section,
Yes.
Sotiris?
Yes, yes. If I am the initial battery, you're right about the relay. The initial battery is discharged in testing lab through cyclers. We have the equipment to do that. All the battery manufacturers have the equipment to do that. Without opening the battery. I'm not sure which connector do you... Yes, the charger communicates with BMS to close the relay. It's batteries manufactured by by us. So we have the chargers, and between the charger and the BMS, there is a communication channel. And that's the way to charge and discharge the battery to our premises. And I think that all the manufacturers have this.
I have tried to make you unmuted, and I think that we can hear you if you talk. I'm not sure though. Although the question now has ended, I guess.
Yes.
Yeah, okay. Yeah, the record of the webinar and the presentations will be shared on our website tomorrow, the latest. Thank you all for your questions. Thank you, Sotiris, for the presentation.
Thank you very much.
Yorgo?
I will not take any time from everyone, so I would like to sincerely thank all our speakers and participants for their valuable contribution and engagement. So you can find any of this information to our website. I hope that you have taken any picture, or if tomorrow that Maria will share this video, you can scan the QR code and you have access to all of our social media. And we look forward to seeing you in our upcoming webinars. We have also joined webinars with another related project in 18th of March, if I'm not wrong. So you can also find this information to our website. And without taking any of your time, thank you everyone, and see you in the next webinar, hopefully.
Thank you.